So hello everyone, welcome to another particular lecture, and in this particular lecture we are actually continuing our previous lecture. So in our previous lecture I have discussed about the radical initiator in brief. So in this particular class we are actually we have to do an elaborate discussion about the radical initiators. So the type of thermal radical initiator that you already know that why actually are using the initiators. Initiator are nothing but that actually in case of normal thermal method of radical generation, that what happened that the radical can be generated in a higher temperature, but but by using an initiator we can drastically reduce the temperature of radical generation and we can generate a radical in a lower temperature. So there are different type of thermal radical initiators are there. So the first type of things are peroxides. The compound like benzyl peroxide, it actually decomposes upon a heating to produce radicals, and these particular peroxides radicals are commonly used in a polymerization reactions. Next is the azo compound. This is the very important. Like example include azo bis isobutyl nitrile, there is a AIBN, which generates radical upon thermal decomposition. And there is another system is there, that is a redox system. Redox system are in some are usually a metal complex, and this particular metal complex are actually involved in a redox reaction between a compound such as persulfate or ferric cyanide type of things with a reducing agent which generates radical in a lower temperature. And in the next slides, we are discussing each of the radical initiator in a descriptive way. Okay. So first we are talking about the peroxide initiators. So the peroxide initiator, the most infamous peroxide initiators are this, like ditert butyl peroxide. So when it will be react in a 25-degree temperature, this particular radical has been formed, and this radical has been formed, and the half-life of this particular radical is 12 hours in 25 degrees centigrade. Similarly, third butoxyl perbenzoate, these particular bonds are actually very much weak, and thus it will do a homolytic cleavage, okay, in presence of 100-degree temperature, and this radical has been generated. And when this particular radical has generated, this will undergo a decarboxylation reaction to generate the phenyl radical, and from this particular uh, perbenzoate group, this two radical has been formed, and the half-life is 20 hours of this particular radicals. Similarly, the dibenzoyl peroxide which generate the phenyl radical, and the half-life is 2 hours in 90-degree temperature. And the third dibutylcyl peroxide, this particular bond has been undergo homolytic cleavage and to form this tertiary butyl radical, and it will be persistent in 100-degree temperature. AIBN. So AIBN as an initiator that we already discussed about the AIBN. AIBN full form is a 2,2-azobis isobutyl nitride, and this is looking like something this. Okay, and the mechanism of generating radical is that in 66 to 72-degree temperature, this particular bonds are actually breaks apart to generate this radical and nitrogen gas. And the driving force to generate this particular radical is to generate this nitrogen gas. Okay, and this is AIBN is a very much handy because this particular this particular compound has observed in a stable solid form, so it will be used in various reaction where thermally radical generation has been observed. Okay, so there is a two different mechanism is there. Like first that this particular bonds are actually homolytic, not homolytic. It is the cleavage of this particular bond has been observed, and to generate this radical, or this particular bond can be only breaks apart to generate the nitrogen gas, and this the radical, and this is the radical which goes undergo chain reactions. Now there is another system, there is a redox system. Redox system has radical initiator. Persulfate ferrous ions are acts as an oxidant and reductant to generate the radical. Simple this particular reaction, there is a peroxide is there, okay, in react with the ferrous ion to generate the radical, and a ferric ion is there. So here ferrous ion acts as a reductant. Now in the second example, here this particular group react with the ferric cyanide to generate the ferrous cyanide and the particular radical, and here ferricyanide acts as an oxidant. Next, we are talking about the photochemical radical generation. Like as we discussed that in case of thermal radical generation, we use initiator, and we already discussed about initiator in brief. So now let's talk about the photochemical radical generation. Now we already know that light can irradiate the bond breaking process if the energy of the light is equal or greater than the bond dissociation energy of the targeted bond. And we all know that in the case of de Broglie formula, the E equal to hc by lambda, the lesser amount of lambda of a light will have the higher energy. That's why basically in the case of sigma bond dissociation, UV light has been used, because UV light having the higher lower wavelength, that is higher energy, and UV light has been used to break the sigma bond. This is the carbon carbon bond or carbon hydrogen bond breaking is done by presence of UV light, and it will generate the corresponding radicals. Similarly, visible light is the little bit of lower energy than the UV light, and it affects the lone pair and double and triple bonds. And the IR having the lowest energy, so that's why it is actually used to irradiate the carbonyls and the heterosystems. So with this, we have to end this particular class. So in this particular class, we are actually discussing uh, elaborately about the thermal radical initiators, peroxide initiator, AIBN, and the uh, redox system as a radical initiator. Now in the next class, we are talking about the stability of free radical, like what is the stabilizing factor of a radical to be persistent. Okay, so thank you for listening. So we have ended this particular class.